Today we're going to talk about phase diagrams. A phase diagram is another kind of graph that we can use to look at the relationship between the three phases and the changes that occur between them. A phase diagram is used to describe the conditions of temperature and pressure where each phase is most likely to exist. So let's see if we can think about general temperature and pressure conditions where each phase is most likely to exist. Let's start with the gas phase. What kinds of temperatures would you need to make a gas? Think about trying to make liquid water into steam. You would want high temperatures. And remember that for a gas, we want the molecules to be very far apart. If they're going to spread out, we need to have low pressures because otherwise they would get squished together. So for a gas, we need to have high temperatures and low pressures. If you think about the conditions needed to have a liquid, you could probably expect that those conditions would be somewhere in the middle. Medium temperatures and medium pressures. On the other end, if we had a solid, like trying to make ice from liquid water, we would want low temperatures, and we would also want the molecules to be close together, so high pressures, low temperatures, and high pressures. We're going to take these conditions and use them to create a phase diagram. A phase diagram is a graph that shows the relationship between the three phases in a sealed container. So here's an example of a phase diagram. You may want to pause the video at this point so that you have time to copy down the labels, including the words, the numbers, and the letters. On this graph, we see three separate areas. For a solid, at the low end of the temperature scale and the high end of the pressure scale. We see liquids somewhere in the middle and gases at the high end of the temperature scale and the low end of the pressure scale. We also have some numbers on here that are used to label the lines, the three segments of lines, and two letters that represent the points, A and B. So let's look at those features in a little more detail. The lines are called lines of equilibrium, and on those lines the substance exists in equilibrium between the two states. The substance exists in those two states at that point, on any point on that line. At that temperature and pressure, both phases exist together. For example, line segment number 1 on your graph represents the solid to gas line. Any point on that line, you would be traveling between a solid and a gas, and both phases would exist together. Same thing for line number 2. Line 2 is the solid to liquid line, and line 3 is the liquid to gas line. So at any point on those lines, the phase on one side and the phase on the other side exist together at that temperature and pressure. When you cross one of the lines on the diagram, that represents a phase change. The next features we're going to look at are the points. The first one is called the triple point. The triple point is one specific combination of temperature and pressure where all three phases exist in equilibrium together. Here's a picture to help you visualize what that might look like. If this represented a sealed container and you had some solid substance at the bottom sitting in the same liquid substance with gas molecules above it, you might be at the triple point. On your graph, the triple point was letter A. That's where the three lines meet, so that's where the three phases exist together. The next one we'll look at is called the critical point. The critical point is the point past which neither liquid nor gas truly exist. The critical point is the end of the liquid-gas line, and past that point, instead of having a separate liquid and a separate gas phase, you get an intermediate fluid phase, otherwise known as plasma. On your graph, this was point B. In case you're curious, a plasma is an electrically neutral, highly ionized gas composed of ions, electrons, and neutral particles. It is a phase of matter distinct or different from solids, liquids, and normal gases. Next, let's look at the phase diagram for one specific substance, and let's use water. The phase diagram for water has a couple of interesting things we could point out. The first being the slope of the solid-liquid line. If you were in math class, you might describe this as a negative slope, almost like it's tilted backwards. Most substances have a positive slope, tilted the other direction for the solid-liquid line. The reason water's is tilted backwards has to do with the fact that solid water, ice, is less dense than liquid water. That's why ice floats. We also have a couple of other points labeled on here. We have 0 degrees C, that's the melting point or freezing point of water, and we have 100 degrees C, which is the boiling point or the condensation point. Those points, 0 and 100, are the boiling point and melting point when you are at standard atmospheric pressure. That's the combination of pressure and temperature where those phase changes occur when your pressure is standard. If you had a different pressure, maybe right here, those phase changes would occur at different temperatures. And we'll talk more about that in the next lecture on vapor pressure. But these labels up here stand for normal melting point and normal boiling point. That's the melting point and boiling point at standard pressure. Just to recap, boiling point refers to the temperature at which a liquid boils, which is anywhere on the liquid-gas line. You can have a boiling point anywhere on the liquid-gas line. The normal boiling point is the specific combination of temperature and pressure where the pressure is standard. So it's the temperature at which a liquid boils at standard pressure. And again, here on the graph, we're labeled NBP. Normal boiling point is 100 degrees C. The melting point, as a reminder, is the temperature at which a solid melts. This can be anywhere on the solid-liquid line. The normal melting point is the temperature at which a solid melts at standard pressure. So when you look at the graph, standard pressure corresponds to 0 degrees C for water. But if you had a different pressure, you would have a different melting point. You'd have a different temperature there. Remember from before that the boiling point can also be called the condensation point, and the melting point can also be called the freezing point. This is because that's the same temperature. Boiling and condensation occur at the same temperature. Melting and freezing occur at the same temperature. It just depends on which direction you're going. Are you on the heating curve or are you on the cooling curve?